Welcome to our channel, my dear students. Today we are going to discuss about the previous years, that is last 10 years CBSE board chemistry questions part 6 in haloalkane and arene, in which we are going to discuss the chemical reactions part. So here the question number 1, which was asked in the year of 2013. What happens when CH3Br is treated with KCN? So as we know that if you write the reaction like this, suppose if I am taking CH3Br here and if it is reacts with KCN, so now we have to see the nucleophile. So here when compared to Br, CN is a strong nucleophile. The strong nucleophile will come and attack this carbon. By the way, this Br minus will get leaves off and I will be getting a product as CH3CN plus KBr. So this product I am getting only because of that strong nucleophilicity of cyanide. And second thing is, why is plus minus butane 2-ol is optically inactive? This was asked in the year of 2013. So first we have to write butane 2-ol. So butane 2-ol, how we can write? So there are 4 number of carbon atoms. 1, 2, 3, 4. So in second position I have alcoholic group. Am I right? So here butane 2-ol. So I have to satisfy with the hydrogen. So here it is the H, here it is the H2 and here it is H3. So 1, 2, 3, 4 butane. Second position I have all butane 2-ol. So now the butane 2-ol, if we see, so this carbon will be considered star carbon, this star carbon. So around this carbon atom, one is methyl group, one is OH group, one is CH2 CH3 group, one is hydrogen. Now this carbon is chiral carbon now. So chiral carbon means it is optically active, but in this case they asked a question, plus minus butane 2-ol is optically inactive. Why? Because if I am taking if these two compounds will be taken in 50%, suppose they taken as plus or minus, that's what 50% of this compound and mirror image of this one. So CH3, here CH and here it is OH and CH2 CH3. Okay, so I am going to write this hydrogen like this. Here also I am going to write the hydrogen like this. You consider this is not a hydrogen. So this will not be matched. So this is not superimposable. Whether it is superimposable or not, if it is not superimposable, they are chiral. But here these two form enantiomers. 50% of these enantiomer, if it rotates the plane polarized light towards to the clockwise direction, because of that presence of these 50%, which will rotate the same polarized into the anti-clockwise direction. That is what it is optically inactive. Are you able to understand, student? Only because of that 50% of this DL isomer will gives optically inactive nature to the compound. And third question, why Grignard reagent should be prepared anhydrous condition? This was asked in the year of 2012 and 13. So why Grignard reagent should be prepared anhydrous condition? Because first of all we have to know what is Grignard reagent. This is nothing but general formula is RMgX. That's a Grignard reagent. If I'm taking a water HOH, so here the charge of metal will be always 2+. If it is 2+, this will be minus, this will also be getting 1 minus. Now this is a polar, so that it got positive, it got negative charge. Okay, now what will happen? Now this R minus will come and attack this and it forms RH. It's not alkane. So when alkane is formed, if water is used to prepare Grignard reagent, that is what we have to avoid. The anhydrous condition, we should not use water to prepare Grignard reagent. That is what we use ether in this case. Okay, along with that I'll getting a product like Mg, and here it is X, here it is OH. Are you able to understand? And next one is predict the order of reactivity towards SN1. As we discussed earlier a lot, SN1, it's nothing but there will be it entirely depends on the stability of carbocation. So carbocation stability, which must be very important in the case of what is that, SN1 reaction. The stability of carbocation, more stable carbocation will lead to react more faster in SN1 as compared to these four compounds. So compound number 1, so it is 1 degree, so it forms 1 degree carbocation. But here compound 2 is 3 degree, it forms 3 degree carbocation. And compound 3, it is also 2 degree carbocation, it forms 2 degree carbocation. And in this case also it forms 2 degree carbocation. As per the order, what is the order? So we have to see the order. So here more steric hindrance. So 2, compound 2, which is more reacts faster in SN1. Why it will be? Because steric hindrance. Okay. And after that, the compound 3, which is having one C6H5, one hydrogen is there. So the compound 3 is the second most reactive. And third one is compound 4. As per the stability order, here it is both the group are C6H5, but here one CH3, one CCH5 is there. That is what it will be reacting faster when compared to this one. That's what the order will be like this. And finally we have 1 degree. So that is the first one. So as per order, 3 degree, then 2 degree, then 1 degree. That is the order. So 3 degree we have, 1 degree we have. So 3 degree will be in first category, 1 degree will be in last category, we know. So in this 2 degree categories are there, in which one will react faster, we have to decide. So here more steric hindrance in this compound 3, that is what reacts more faster in SN1. And next question, which will react faster in SN1? As we know that SN1 which means that the stability of carbocation. Here 1 bromobutane, here I written the structure of 1 bromobutane, here it is a 2 bromobutane. So here it is 1 degree, it is 2 degree. As per the stability order, 3 degree will faster in SN1 and 2 degree, and then it is 1 degree. According to that, this 2 degree will react faster in SN1. And next question, explain the following reaction with example and mechanism. They asked Friedel-Crafts reaction. They explained the following reaction with example. This was asked in the year of 2010. Now, the Friedel-Crafts reaction. What is Friedel-Crafts reaction? Either it is alkylation, or it may be acylation. Alkylation or acylation may take place. What is alkylation? So the addition of alkyl groups to the ring. Now Friedel-Crafts reaction. What is the Friedel-Crafts reaction? Suppose if I am taking a benzene ring, okay, in which I am going to add CH3Cl. So I am going to adopt the CH3 group in this. So I am going to prepare benzene to toluene. How will you prepare it? So in presence of, I have to use anhydrous aluminum chloride. This will act as a Lewis acid. Now here it forms electrophile. So it is a kind of electrophilic substitution reaction. So now we can shall we see the electrophilic substitution reaction? The overall product, what I'm getting here is, so this is the product I'm getting. So what is that? So here it is, CH3 group is getting attached with this. So this is benzene to toluene I'm getting. Okay, so how we can see? So in this case of acylation, the thing is, instead of these, suppose if I'm taking a benzene, So instead of that methyl chloride, I'd like to take acid chloride. Same in presence of anhydrous aluminum chloride, I'll be getting acylated product. That is C double band O, CH3 I'm getting. Okay, now let's see the mechanism, how it happens. So here benzene ring I'm taking. Okay, so here 1 bond, 2 bond and 3 bond is there. So before that, here the electrophile is getting formed. How the electrophile is getting formed? Now the anhydrous aluminum chloride AlCl3 will react with our CH3Cl. It forms AlCl4 minus, because it's a Lewis acid, and CH3Cl, and the CH3 plus is there. Okay, this CH3 plus will act as a electrophile. This electrophile will, now the bond will break, will come and attack this electrophile to form our product. Now we can see how it happened. So here it is, CH3 plus is there. Okay, now the bond is getting breaked. Okay, suppose the bond is getting breaked in this fashion. Now what happened? Here one side will get positive charge, the head side we are getting negative charge, the tail side we are getting positive charge. According to that, I will be getting a product like this. So what the intermediate I am getting? So here this bond will not change, this bond will not change. This only getting break. Here it got negative charge, here it got positive charge. Okay, are you able to understand? Now the CH3 plus will come and attack here. That is, this is going to attack. Now what happened? Now what will happen? So here this will be getting attracted. Now what happened? So here one bond is there. Here one positive charge is there. Already one hydrogen is there. Now CH3 plus will come and attack like this. Okay, one hydrogen is there. In all this case, benzene is C6H6. In all the place we are having one hydrogen. Now if CH3 want to come, it replaces this hydrogen. The hydrogen wants to move, at that time only this CH2 will come and attack. Okay, now what happened? This H plus wants to move to form stable compound. So now if it leaves, this bond is getting break, the H plus will move, so I'll get negative charge here. Now this negative charge and this positive charge will form a bond to maintain a aromaticity. Now I'll get a product like this, CH3. So this is a alkylated product. In the case of acylation also, I'll be writing the reaction only. Now AlCl3 will react with Cl, C double band O, CH3. This is acyl chloride. So what I'll get the product here, AlCl4 minus, according to that, CH3, C double band O plus I am getting. This will come and attack in the same mechanism. By that way it forms acylated product like this. Okay, so here I written for alkylated product, so you have to try it for acylated product. So thank you so much for watching. So please subscribe my channel. So please go forward to others to get benefited. So thank you so much for watching. Thank you once again.